Uh, Hello, good day. So, for AMK20102, this is our first video or session. So, before we go into each of the to each of these chapters, so let's take a look on the teaching plan. Teaching plan for this subject. What I want to emphasize is this course summary. So this course should provide you with a clear presentation of theory and application of structure analysis as it applies to beams, trusses, and frames. And then it introduces analysis statically determinate. So statically determinate structures for beams, trusses, and frames. So you should be able to analyze the structural statically determinate structures. And beside that, it also introduces deformations analysis, which we will learn in later chapter, of a statically determinate structures using visual work method uh, for trusses, beams, and frames. So we have two learning outcomes, which is to CO1 is ability to evaluate the internal members. So you should be able to calculate the internal members and deformations, and then for determinate structure. And then CO2, you should be able to build a sustainable bridge model, which is to design a bridge and build a bridge. So in this topic, in this course, we have uh, 14 weeks, but in this short sem, we only have 4 weeks. But it covers the introduction on structural theory, and then analysis on statically determinate trusses system. So we will take a look on the analysis of statically determinate trusses, and then statically determinate frame, and then later on continue with the work energy method to analyze the displacement and then the movement of the structure, deformation, and then we will analyze the deformation of a beam using the virtual work and then a frame using the virtual work. So that's that's all the topic uh, contained in this course. So let's start with the first chapter. So the first chapter is the introduction to structural theory. So we have five subtopic. We want to know what is the idealized structure, and then the principle of superposition. This is our theory before we going into the analysis, and then equations of equilibrium. How to you come up with the equation of equilibrium in order for you to analyze the structure, and then the degree of determinacy and stability of a structure, and then let's see how we apply the equation of equilibrium. This first subtopic, idealized structure. Uh, Idealized structure is to develop the ability, technique to model or idealize a structure so that the structural engineer can perform practical. You want to perform a practical force analysis on the members. So basically, when you have a structure, a real structure, you want to build. So you want to idealize it. You want to model it or idealize it so that it will be easier and practical to be analyzed. So in simple word is that you want um, to convert lah, somehow convert structure to become more simplified. You want to simplify a structure. um, let's take a look at the support connections. Usually we have pin connections, roller support, and fixed joints. So these are all idealized. Sometimes the connections are not this idealized, not totally pin, not totally roller support, not totally fixed joint. But in analysis, idealized structure, we simplify it to become a certain support to become a fully pin connection. When it's a pin connection, uh, then you don't have any moment rotation restriction. And then if it's a roller, then you have the moment, and then also the vertical. You don't have the vertical um, you don't have the vertical restriction against the movement. And then fixed joint, there will be no relative rotation. So as you can see here, this is the typical pin supported connection method. So this is the actual that we are building, but in the idealized, uh, there will be there will be no moment restriction. But as you can see here, you might visualize that there is some restriction in the moment, but in the idealized structure, there is no moment. There is no moment for pin structure. But for the fixed supported connection, then you have moment, and then the lateral restriction, and then the vertical restriction. And this is the typical roller type connection for concrete, usually at bridges. This is the usually the fixed supported connection. Mostly that is well used in construction of houses. They use a monolithic fixed supported connection concrete. So this is the idealized structure. So you have pin supported, pin connected joint, and then a fixed support, and a fixed connected joint for frame. This is also for frame. And then this is a torsional spring support and torsional spring joint. Support connection. In reality, all connections exhibit some stiffness, as I said before. There was some stiffness, but in idealized structure, we idealize it to become fully. If it is spin, then it's spin. There will be no some stiffness or restriction at moment against rotation. So this is the idealized structure. For spring, like this one, spring you have K. If it is the K value spring joint is 0, then the joint is considered pin. There's no restriction in the rotation movement. But if the K spring value has a value, then we consider the joint is fixed. Then we become a fixed joint. When selecting a model for each support, the engineer must be aware of how the assumption will affect the actual performance. So basically, when you want to assume a certain support, so you should uh, be aware of the implication of your assumption. For example, if you assume there will be no restriction in the moment, so the implication will be there will be less support reinforcement of steel in that structure against moment at the connection. So that will be the implication. So some of the designer in America, they would, if like a steel structure, if the connection have some sort of some value of restriction against a moment, so they would consider a certain value of forces being converted into moment. So, but in, the, in this subject, we only concern with the idealized structure. But later on, when you are working, so this need to be put into consideration. Analysis of the loading should give a result that closely approximate the actual loading. So the loading should closely, but again in designing, we have a factor of safety we add to the loading. So basically we slightly over design, but not too much. The support connection, in reality, all support that is distributed surface loads on their contacting members, but we assume there's no surface load or bearing loads. When surface in contact, there will be some load on the support. So but in the DLS structure, we don't uh, assume there is no load in that part. It's a load directly applied on the support. So these are all the type of connections. A light cable, so it will be a joint. I think it's a pin, and then rollers. You have three types of three types. These can be considered rollers, where you have only reaction, vertical reaction. There is no reaction horizontally. There is no horizontal because the frame can move vertically. And this is also considered a roller. This is a smooth pin connected collar. You have pin here and then a fixed support here. And then this is the pin and so on. So wildlife structure, let's take a look at example. Consider the jeep frame. This is a jeep frame and trolley. This is trolley. So we neglect the thickness of two main member and we'll assume that the joint at B is fabricated to be rigid. So this is fixed joint. So you'll be have reaction vertically, horizontally, and then a moment. The support at A can be modeled as fixed support, which is similar. These 2 points is fixed support. So when you draw the free body diagram of the idealized structure, it will become like this. So like this. This is fixed. This is fixed. Then this is your movable load, which is a trolley. And let's take a look at the framing. The next is a framing. Consider the framing used to support a typical floor slab in a building. A slab is supported by floor joists located at intervals and they are in turn supported by two side girders A, B, C, D. So this is your floor slab. Yes, and then supported by a floor joist. And then these are in turn supported by the two girders. These are two girders. Girders A, B, C, D, A, B, C, D. So for analysis, it is reasonable to assume that the joints are pin and or roller connected to the girders. And the girders are pin or roller connected to the column. So we assume that this joist is connected by pin to this girder and this girder is connected pin to the column. That is the simple way. We eliminate the unknown moment that could occur at the joint if it is a fixed joint. Okay, next is a tributary loading. So when you have a slab like this, so how are the load, if you have load here, how are the load being distributed to the girders? How much area, how much load being distributed to AB and how much is distributed to CD? So this is tributary loading. How the loadings being distributed. So there are two ways which the load on the surfaces is transmitted to various structure elements. So the first one is one-way system and the second one is two-way system. This will be repeated in your RC design, so better pay close attention. Tributary loading is one-way system where you divide into two. Basically, you divide into two. So the loading, basically, you can idealize it to be distributed into two beams. As in this case, is the load, the slab is being reduced, being idealized into a beam. So the beam CD, C and D, which is C and D. So you distribute the load from the slab, which is 4.8 kilonewton per meter squared. So you times by the tributary length or the length being separated. In this case, it is a one-way system. So slab AB, as you can see here, being split into two. So the total length between B and D is 1.5 and 1.5 here and another 1.5 here because the total is 3 meter. So 1.5 divided by 2 again, then it will be 0.75. So 0.75 times 4.8, then you get actually 0 on CD. There are two area. You have one here, and another one is on the other side of a beam CD. So you have 1.5 times 4.8, then you get 7.2 kilonewton per meter. So distributing load. So that's how you distribute your loading in the one-way system. So basically, if it is a slab, it will be UDL, uniformly distributed load. So next is a two-way system. Two-way system. So basically, one-way system, you're being supported at one edge, at each edge, one edge. So something like that. But in two-way, you're being supported in two axes. Two axes. So basically, four beams are supporting the slab. So how do we distribute the load? So we draw the 45 degrees line. For example, this A, B, D, C. And basically draw the 45 degrees load. So we draw the 45 degrees load. So these are the areas that carry the loads from the slab onto the beam. So you have this distributed load, but a triangle distributed load. So the peak happens at the most area. So the biggest area is at the mid-section. So as you can see, the peak is at mid-section and reduced up to the column of A and B. So how do we calculate 7.2? Uh, because of the length 1.5, the peak here 1.5 meter, then here is being reduced because the distance, the distance between of the area is being reduced. So this one is 1.5, and then it's reduced up to 0. So they have 0 loading at the A and 0 loading at B, and the peak at the mid section. So that's the whole concept on designing, on idealizing a structure. Let's take a look. Example, the floor of a classroom is to be supported by the bar joist as shown. So the bar joist here. This one, joist here. This more, it looks more like a roof. So each joist is 4.5 meter long. This is the length of the joist, and there are space between joists. Center to center is 0.75 or about 3 feet. The floor itself is to be made from lightweight concrete. That is 100 meter thick. So basically, this is to show you the loading, the self load from the lightweight concrete. Because the thickness is given, neglect the weight of joist and the corrugated metal deck, and then determine the load that acts along each of joists. So let's take a look at this example. So this is the 3D model. So you have spacing between joists 0.75. So basically it's a one-way system as shown here. So you take, each beam will take half and half here, half on the right hand side and half on the left hand side. So total 0.75, which is the spacing center to center. And then the length is given here 4.5. So based on this area, this width and this length, so you can get the area. Basically 0.75, the length, the breadth, the breadth times with the as you show here, how we calculate the loading. So that load, weight of concrete slab is equal to this is the thickness thickness of the lightweight concrete times by the density, density of concrete. So you get kilonewton per meter square, the density at the dead load of weight concrete slab. And then live load is it's not given here, but actually it's in the table. Given by design code. Design code is not shown here. But it's okay. So the live load is actually typical for a school or office structure. So floor live load will be given by the design code. So 1.92. So the total load is total up this dead load and live load, but it differs each based on the design code. Some design code put some weightage in front of the live load and total load and the dead load, but without the factor of safety. So this is your loading 3.42, so times your load, and then uh, the ratio between the breadth and length is used to determine the type of slab we are facing. So your L1 is 0.75 here, and then your L2 is 4.5. So divided to 0.75 and 4.5, you get the value is more than 2, which is considered as a two-way slab. So when it is two-way slab, so the loading is more simple, and then there's no need to draw a 45 degrees like this. And then uniform load is calculated. So the loading times the breadth, so you get your UDL, uniform load across the joist. So after we have analyzed the loading, so we can calculate the reactions. The principle of superposition. This is the next subtopic. Principle of superposition. The total displacement or internal loadings at a point in structure subjected to several external loadings can be determined. So you want to determine the displacement or loading or stress, the displacement or stress at a point, let's say point A, at a point in a structure subjected to several. So you have many loads, many type of load. Yes, you have a UDL, and then you have a point load. So several external loadings. So you have several external loadings. The displacement and the stresses can be calculated by adding together the displacement or internal loading caused by each of the loads acting separately. So basically, if you have loading like this, so you can calculate the total displacement by analyzing it separately. So you first maybe analyze the displacement due to this point load, and then you analyze the displacement due to distributed load. So you combine each of the displacement of stress. For example, displacement 1 plus displacement 2. So you get your total displacement. So basically, the principle of superposition is that you can analyze a structure if you have many types of loading acting on the structure. So you can analyze them separately. And when you analyze them separately, getting a separate value of displacement. So you add all the displacement, you get total displacement for the structure. A linear relationship exists among loads and stresses displacement. And two requirements for principle to apply is that material must behave in a linear elastic manner. So as you learned before in strength of materials, so you have a structure a material that behaves within this elastic elastic area. So beyond this elastic proportionality, they will go into yield. So in applying your principle of superposition, your material should behave within this section of material. So basically, your stresses applied on that material, for example, steel, cannot exceed this elastic proportion, this elastic value stress. So because beyond that, within the yield region, the steel won't go back into its original uh, behavior, and the stress strain, the modulus of elasticity is at that point the modulus of elasticity doesn't apply anymore. So the steel will behave in plastic deformation. So uh, as the strain increase, the stress will increase. Basically that. So within the principle, this principle only applies for material that behave within this linear elastic manner. And the geometry of structure must not undergo significant change when the loads are applied. So the geometry, say uh, this square, after you apply the load, and then it becomes non-square anymore. So the load being applied is not toward the axis anymore, and when that happens, the principle of superposition is not applied, it's not applicable anymore. So these two requirement need to be fulfilled before you apply for principal superposition. Of course, if you cannot fulfill the requirement, then the analysis, maybe using finite element analysis. Equations of equilibrium. So this is the next topic, which is very important. We'll continue in the next video.